Hello, it's Mr. Kaladi here, and today we're going to slow down a little bit and we're going to just talk more about the derivative and make sure we understand it a bit better, because we've done a lot. We've used limits to find a derivative, we have all these derivative tricks, but we shouldn't go any further unless we're really comfortable with what the derivative is. So, we're entering Mathville, please derive carefully. Okay, so let's consider a quadratic. Here it is, x squared minus 6x plus 5. If I factored this, it would be what? Y equals x. It would have to be minus 5 and minus 1, I believe. And then there it is. I've graphed it down here. I've gotten Desmos to graph it to save us some time. What's the derivative here? Well, y prime is equal to, bring the 2 down, so 2x minus 6. Again, so what is the derivative? Or specifically, why is there an x in the derivative? Well, remember, the derivative is the slope of the curve. It's the slope of the tangent line. And the slope for this quadratic changes with every value of x. So let's write that f prime equals 2x minus 6 is the derivative function derivative function. It tells us the slope of the tangent line, that is, aka also known as the instantaneous rate of change, at any point on the original function. So, for example, at x equals 0, what is the slope? What's the slope of the tangent line? Well, I would I would sub x equals 0 into this equation. So 2 times 0 minus 6 gives me negative 6. And where's 0? Right here. If I were to draw that, indeed, it's correct. Look, the slope at that point, at x equals 0, is indeed slope of the tangent is negative 6. Okay, what about, let's try a different one, at x equals 1. Well, slope of the tangent is 2 times 1 minus 6, so that's 2 minus 6, so that's negative 4. Let's look at x equals 1, so right here, I'm not going to draw it because it's going to get too messy here, but you can see that the slope would be not quite as steep. Let's do another one at x equals 2. Slope of the tangent is 2 times 2 minus 6. That's negative 4. Or sorry, negative 2 rather. And where's 2 is here. There's the point x equals 2. And this tangent would look something like this. And you could see that m of the tangent is equal to negative 2. It's definitely not as steep. It's the slope of negative 2. Here's an interesting one. What about x equals negative 3? M tangent is equal to 2 times 3 minus 6, which gives me 0. Well, what does that mean? Well, the slope of 0 means a flat line. And, oh yeah, look. At this point, x equals 3, the tangent is horizontal. So there's a few things to observe here. Look how the slope changes. And I get that changing slope from using my derivative function. The other thing, what do you notice about all these numbers? They're changing by a linear amount. And that's no accident. In fact, if this is my quadratic, so f of x is equal to x squared minus 6x plus 5. If I were to graph the derivative function, 2x minus 6. So I'd be graphing all these numbers. Well, at x equals 0, we already figured it out. It's negative 6 down here. At x equals 1, it's negative 4. At x equals 2, it's negative 2. At x equals 3, it's 0. That's actually a line, right? It's a linear equation. My derivative function, that is 2x minus 6, is linear. And my original function was quadratic. This is no accident or surprise or something that we should not take, that we should not consider. Like, this comes up. If I take a function, polynomial function, its derivative function is 1 degree lower. We go from second degree to first degree, quadratic to linear. This is going to come up a lot in grade 12 when we return to calculus. For now, I'm just going to introduce the idea that we can figure this minimum point out. We can find this minimum point by considering that it is the point where the slope is 0. What we're going to find a lot in grade 12 is that, hey, if you want to know the minimum point of a function or the maximum point, just look at its derivative function. Find the point where the derivative is equal to 0. This corresponds to the minimum point on f of x. This is something that's going to come up in the later calculus chapter, but to find this min or max point, I just find when my derivative is 0. This is going to come up in the optimization chapter. So that's kind of just a preview to show you where we're going. But it is worth noting that the relationship between the two. It's also worth noting that this is a negative slope, negative slope, negative slope, and you see how the slopes are all negative. Here I have a positive slope, positive slope, positive slope, so my derivative function is positive. So really the derivative function tells you if the original function is decreasing, going down, or increasing, going up. So those are just a few observations we make, just kind of to set us up for future calculus. Observe how the degree of f prime at x is 1 less than the degree of the original function. Oh god, oh so sorry. Okay, that's one neat observation. The second neat observation is, well, the second application, I guess, and again, we'll do this in grade 12, but this is just an introduction. If I have a function like this is a fourth order function, and someone says to sketch the derivative function. So this is f at x. How can I sketch the derivative function? Well, we know from the given graph, where the slope is 0, right? Like we just learned up here. When we reach a min or a max point, we have this kind of balance point where the slope is 0, the tangent is 0, the derivative is 0. So on this graph, you can see there are actually 3 of those points. There's one right here, looks at like what, negative 0.5. The slope of the tangent is 0. There's another one up here, at what, 1.5 or something like that. 1.5. M is equal to 0. There's another one here, I don't even know what it is at. .3. So we know that the slope is 0 at x is equal to, so this is 1.5, so we'll say 0.25. X is equal to 1.5. and we'll say 2.3. I don't know, approximately. So those points correspond to a derivative function where the derivative is 0. So here the derivative is 0, here the derivative is 0, and 2.3, the derivative is 0. So we know from my derivative graph that there are those points. Actually, I'm going to draw them as x's. Doesn't really matter. Okay, remember we're trying to draw the derivative. So far I know 3 points. Okay, the next thing we can look at is this idea of increasing or decreasing. So also, the slope is positive let's look. Well, the slope of my original function is positive here, right? It's all the slopes. If I drew all those tangent lines, they'd all be increasing, or they'd all be positive. Sorry, they'd all be positive. Same with here. So what are those regions? Well, this would be from x is between 0.25 and 1.5. So when x is between 0.25 and 1.5, and when x is greater than 2.3. During those times, the slope is positive, and therefore the derivative has to be positive. So if you think about it, then in this region, I have to cross this point and this point, but I have to be positive. I don't know what the exact y value is, but if I sketch this, it has to be positive. Similarly, this has to be positive. The converse of this is when m is less than 0. When is there a negative slope? Right? Can you imagine? All the tangent lines here are negative. That means my derivative is negative when x is less than, what was that x value? Oh my god, it's negative 0.25. Oh, it's like negative 0.25, negative 0.25. Less than negative 0.25. It's negative for all those. And it's also negative between 1.5 and 2.3. 1.5, x is between 1.5 and 2.3. So when I graph my derivative, again, for this region, the slope is also negative. So it goes on forever. It's always going to be negative. Here it's going to be negative, but it has to go through this intercept, and then it continues. Neat. Again, look what happened. We have here a fourth order, and this is the derivative, and no surprise, it's a third order. It's cubic function. We always go down in degree. What we just did here, this idea of going from one function to its derivative function using the properties, this is curve sketching. And this is a whole chapter we're going to do when we return to calculus in grade 12. So you get an idea of the two kind of things we're going to be doing: finding max-min points and graphing functions. Hopefully you have some understanding of these things, but we're going to be spending a lot more detail on them. Let's go over to some of the questions that you're going to see in this, more specific questions that you'll see in this part of the course. So I have a function, y equals some cubic function. I want you to find all the points where the slope of the tangent is horizontal. So now we have to think a little bit. So what does this mean? I want to find where the slope of the tangent is horizontal. So find where m tangent is equal to 0. Now, m tangent, well, that's just the derivative. So in other words, I need to find where dy dx is equal to 0. So that's what I'm trying to do. Practically, I'm trying to find these points, right? Sorry, where the tangent is 0. So I need to set the derivative equal to 0. So let's start with my function. Here it is, y equals x cubed minus x squared minus x plus 1. Let me find my derivative. That's usually how a calculus question works. And now I'm going to set that derivative equal to 0, because I'm trying to find where the tangent line is 0. Has a slope of 0. So now I end up with 0 is equal, oops, sorry, this is 3x squared. Well that's just quadratic. I'm not even doing calculus now. This is 0 is equal to, okay, let me see if I can factor this by inspection. Well, these are both going to be 1s. They have to be. 1 has to be positive. So this one's going to be positive. Nope. The negative wins out. So sorry, this should be negative and this should be positive. So we end up with 3x plus 1 equals 0, which gives me x is equal to negative third. Sorry about the space management. And here we end up with x equals 1. So embarrassing in the space. Okay, so what did we just find? Find all the points where the slope of the tangent is horizontal. So I just found the x-coordinates where the slope is horizontal. Again, what I just did is found basically x equals whatever. That's where the slope is horizontal. But I need to know the actual point. So I need to find the y value. So I need to take the x value I found and sub it into the original equation. We need the corresponding y values from the original function. So let's sub in x equals negative a third. So then what's y going to be? Well, y is going to be negative a third to the power of 3 minus negative a third squared minus negative a third plus 1. Oh, what a pain. Well, I have to do it anyway. So I guess this is going to be 1 over negative 1 over 27. This is going to be negative 1 over 9 plus 1 over 3 plus 1. Dot, 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 dot. Well, I've already done this, so I'm not going to do it again because it's a lot of work. But it's 33 over 27. And you can do it yourself. And then you sub in x equals 1, and you get y equals 1 to the power of 3 minus 1 squared minus 1 plus 1. And that gives me 1 minus 1 plus 1 minus 1. So 0. So therefore, the slope is horizontal at points negative a third, 33 over 27, and 1 comma 0. There we go. So this sort of question is common in this chapter where you have to understand how to manipulate the derivative to find some sort of point or something like that. Let's do another classic IB example. Find the normal line to this curve when x equals 9. Well, a few things are going on here. First of all, what is a normal line? Well, I think you did it in grade 10, but I'm just going to go through it again. We're going to make sure notes are complete. Better be a little more careful with my space this time. I really screwed up above there. Just acting like there's tons of space on this page. Let's just graph this. So this is what kind of graph? Well, it's a square root function, and it has a 2 in front, which is a vertical, because outside the bracket, it's a vertical stretch by 2. Regardless, the graph looks something like this. F of x is equal to 2 root x. And we want to find the slope, or the normal line, at x equals 9. So let's say x equals 9 is somewhere here. 9. And, okay, let's talk about normal line. So the tangent line is the line that touches the curve and approximates the slope. So that is my tangent line. Tangent. What is this point? It's 9, comma, if I sub in 9, it's 6. Okay, here we go. Now the normal line is the line that is perpendicular to the tangent. So it's at a 90-degree angle to the tangent. Normal is something that comes up in science sometimes. You hear about the normal force, which is perpendicular to the surface. Normal when you're doing optics, I think, sometimes. Normal ray. So anyways, the normal is 90 degrees to the tangent line. So this question is saying, find the equation of the line that is 90 degrees or perpendicular to the tangent line. So there's a lot to do here. Before we go on, what's the relationship between the normal line and the tangent line? Hopefully you remember from grade 10. Recall that a normal line is perpendicular to the tangent line. But they both go through the same point. So they both go through the same point here. But, sorry, what's the relationship between the two? Well, the slope of the normal line is the negative reciprocal of the tangent line. Hopefully you remember doing this in grade 10, right? The slope of this line is negative 1 over the slope of this line. That's how they're related. The negative reciprocal. You have to remember how to do this. If you want me to write this out in words, the slope of the normal line is equal to the negative reciprocal of the tangent line. So that's, oh geez, okay. So that's our little aside, like we should kind of, I'm gonna put this in a little box here so we don't forget. Just so that you're aware, because again, the normal line is a very common thing to be asked. So now we have to find the equation of a normal line. So there's a few steps we have to do. Well, first of all, let's work on the slope. So I don't know the slope of the normal line, but I can find the slope of the tangent line. So the first thing is find the slope of the tangent line, which is, in other words, find the derivative. So if I have my function f at x is equal to 2 root x, which is, let's just rewrite it as 2x to the half. Well, my derivative is 2. I ignored the 2. And then I bring the half down, so half x, subtract 1, so I get negative half. So I end up, the 2 and half cancel out, so I end up with x to the negative half, which is really 1 over square root of x. That's my derivative function. So therefore, m tangent is equal to 1 over square root. M normal, which is what I'm looking for, the slope of the normal line, well, that's the negative reciprocal, so negative 1 over that. So, for the equation of the normal line, it should be y equals mx plus b. Well, oh boy, there it is. I know what the slope is. I just have to use that equation. And so let's do that. We're looking at x equals 9. So at x equals 9, the slope is negative square root of 9, which is negative 3. So we found this slope. So we need a slope. We also need a point at x equals 9, y is equal to, and that's what we did over here. We subbed it into the original equation. 2 root 9, which is 2 times 3, which is 6. So therefore 0.96 is on the normal line. Right? Like what I just did is if I want to draw this normal line, or if I find the equation of it, well, I know the slope, I need a point. Well, I know a point. It's this point here on my original graph, 9, 6. So I sub the 9 into this equation to figure out what the y coordinate is. Now I have a slope and I have an x and a y. So sub both of those into y equals mx plus b. So I have 6 is equal to negative 3 times 9 plus b. 6 is equal to negative 27 plus b. B is equal to 33. Therefore, y is equal to negative 3x plus 33. Or, conversely, if you want to do that shortcut, remember I told you m is equal to y minus y1, x minus x1. Cross multiply, mx minus x1 is equal to y minus y1. So I get negative 3x minus 9 equals y minus 6. And that's also an acceptable answer. Okay, so those are kind of the classic type questions you're going to see. Manipulation of the derivative to do things that really you would never have to do in real life. Like it's very abstract, but you have to be able to manipulate the derivative. There is always some confusion, you know, do I sub the 9 into the derivative formula or the original formula, so the original function. So sometimes you'll get confused that way. Another common mistake is to forget to take the negative reciprocal when you're finding the normal line. Now, we are going to do an advanced question. Sometimes you might see a question where you have to use a skill that another skill. So we're going to show you that question. We'll do this advanced one. Don't be too intimidated by it, but it's good that you see it. So, tangents are drawn from point 0, 3 to the curve negative 3x squared. Find the points at which the tangents touch the curve. Oh, I've given you the answers. Oh, we don't have to do it then. Okay, this is 2.2.3, page 3. Advanced example. Okay, so let's draw this, because that's where the kind of difficulty comes from. And really, when you're stuck on a difficult question, what can you do other than draw it? So x, y coordinates. Okay, so we have a point 0, 3. Okay, I can draw that. That's somewhere up here. And I have a curve y equals negative 3x squared. So that is a quadratic that opens down, that's been stretched vertically by 3. So I'm going to draw, I guess, that quadratic. It looks something like this. Okay, and that is, there we go. So now it says tangents are drawn from this point to the curve. Oh, so I have to draw a tangent to this curve that also goes to the point. So, oh, so there'll be one like this, basically. And I guess there'll also be one over here. I guess these are technically lines, so they go on. And there we go. Okay, so now here's the tricky thing. There are two points here. What I need to do to solve this question, because I don't know, I can find the derivative of this curve, but I don't know exactly how that links up with the 0.3. I guess I could show you that. Let's start with that. First, we can find the derivative function. Or just the derivative, we would say. So for y equals negative 3x squared, dy dx is negative 3 times 2x, so that gives me negative 6x. So I know, therefore, that the slope is equal to negative 6x. However, I don't know what x value this occurs at, right? Like I want to find the equation of this line, but I don't know what point this is. So I'm kind of in trouble. But this is the technique. This is the more advanced technique. So what we're going to do is label this point. We're going to call it Px comma y. Now, we know we're going to keep calling it x, but we know the y value, the y point on this curve. Well, to get it, I take the x value and I square it and multiply it by negative 3, right? To find the y's, this is the function. So the y is technically negative 3x squared. I can label the function. I guess I never labeled it. It's y equals negative 3x squared. So this point, this random point, every point, in fact, on this curve, you have an x value, and then you do a bunch of things to the x to find the y value. So that's true of every point, including this theoretical one where it intersects, and this theoretical one where it intersects. Second, define a general point P on the function. So that's Px and negative 3x squared. Now, we have 2 points, P and 0, 3. Find the slope of the tangent line. So now we have 2 points on this tangent line, 0.03 and P. So we can find the slope of the tangent line. Remember, slope is just the change in y over the change in x. In other words, I take my y value. So let's take negative, I'll write that, y2 minus y1 over x2 minus x1. So I take y, negative 3x squared minus 3 over x minus 0. If I simplify this a little bit, I get negative 3x squared minus 3 over x. Oh my god, you couldn't see any of that. Okay, so I have these 2 points. I've used the 2 points to find the slope. So now I have the slope of the tangent line. And I also have the slope of the tangent line, which I've already found. So we have 2 expressions for m, which is the slope of the tangent. So set m equal to m. So I have negative 6x is equal to negative 3x squared minus 3 over x. Oh, this is great. Now I have a situation where I have an equation and only one unknown. So using math, I should be able to solve this. First of all, I'm going to cross multiply. So negative 6x squared is equal to negative 3x squared minus 3. Let's collect all of my like terms. So I'm going to bring this to the other side. So I have 3 is equal to 3x squared, I believe. Yeah. And then I divide both sides by 3. Actually, it's a quadratic, so technically I should solve it by factoring. Right? You shouldn't, remember I showed this a while ago. So I have 2 solutions, x equals 1 and x equals negative 1. What is x again in this case? X is the point, these are the 2 points where my tangent line is at this, where the tangent line from this point touches the curve. Now what was the question asking? Find the points where we touch the curve. Well, we have the x values, so we need the y values. So at x equals 1, the y is equal to, well, you can't see, y is equal to negative 3, 1 squared, which is negative 3. And at x equals negative 1, y is negative 3, negative 1 squared, so it's also negative 3. Therefore, my answers are 1, negative 3, and negative 1, negative 3. Whew, so neat. This is a tough question. What is it? Why is it tough? Because you have to use this general point. So you'll see, and we'll talk more about when we study for IB exams, there are certain questions that get more difficult, like question 6 is tougher than question 5, tougher than question 4. So what we've seen before, the previous questions, so question 3, question 4, this question would be question 6. So you might not see it, but if you did see a tough calculus question, they might give you something that requires this skill. I hope that made sense. I gave you one other advanced example you can work on if you want to try to challenge yourself. But the homework I want you to focus on is page 207, number 1 to 5, and 210, number 7 to 10. Good luck, and we'll see you next time.